Okay, so the plan for today is to run through examples of the 8 objectives this week, and then also to run through a practice quiz. So the first objective is asking you to write a chemical equation given a written description. So the important thing is that you know what are the reactants and what are the products. So it says nitrogen dioxide gas is formed. So that means that nitrogen dioxide is a product. And then it says it's going to be formed by the reaction of, so now it's describing what the reactants are, and so then it says nitrogen monoxide and oxygen gas. And the important thing to remember here is that oxygen is a diatomic element, so that's going to be O2. So at this point you need to balance, and you might be able to see immediately what the issue is going to be here is that we have an imbalance amongst the number of oxygen atoms. So what I've got is I've got 3 oxygen atoms on the left here, and then I've got only 2 on the right. So how can I kind of make that work? Well, if I put a 2 there to increase that, then that would become 4, and well, that would be a problem, wouldn't it? But then I could get the other side up to 4 if I put a 2 there, so then we'd have 2 oxygens plus another 2 oxygens, so that would be 4. Now of course the problem is now that the nitrogen atoms, actually no, it looks pretty good, doesn't it? 2 nitrogens and then 2 nitrogens. So that's how we're going to balance this guy. Now I want to have a quick look, see if I can simplify my coefficients, and I can't. So there we go. Alright, so 2NO plus O2 gives 2NO2. Now that's a gas, oxygen is a gas, and NO is a gas. So just getting the correct phase labels there. Alright, so this problem is asking us to tally up the total number of hydrogen atoms on the right hand side. Now it's also important to realize that this should be the same as the number of hydrogen atoms on the left hand side. So let's have a look. This compound here contains hydrogen. There are 8 units of the whole compound, and within each unit there are 4 hydrogen atoms. So that gives me 32 for that guy. And then we've got 3 units of this compound here, and within each unit of the compound there are 3 hydrogen atoms. So that gives me another 9 hydrogen atoms. So we've got a total of 41 hydrogens. Going pretty well so far. Now, if I want to double check, I can tally up the hydrogens on the other side, and it should also come up to 41. So 5 plus 18 times 2, that's 5 plus 36, you guessed it, 41. So doubly confident there. Alright, we need to zoom in a little here. So this is balancing using non-interfering coefficients. So this really means is that it's going to be nice and easy. So if you did the extra credit assignment this week, you would have noticed that there was like level 1, level 2, level 3 in that little game. And level 1 and level 2, you're dealing with non-interfering coefficients. And then level 3, you're dealing with interfering coefficients, and it gets a little bit more difficult. So let's start just balancing atoms left to right. So 2 nitrogens on the left and only the 1 on the right. So let's just put a 2 there and get that fixed. And then hydrogens, we've got 2 on the left, and then we've got 2 times 3, 6 on the right. So let's put a 3 there and fix that. So that looks good to me. 1, 3, 2. Okay, well, cruising at this point seems almost too easy, doesn't it? Okay. Balance the following, and sure enough, there it is, interfering coefficients. Alright, so we've got CH3 plus O2 gives CO2 and H2O, and this is a classic combustion reaction, a reaction involving oxygen that goes on to form an oxide. Okay, so let's just start balancing left to right. I'm going to go here, so carbons, I've got 2 carbons there, and I've only got 1 on the right, so let's just make that balance. And then hydrogens, I've got 3 plus 3, so 6 on the left. And then I've only got 2 on the right, so let's just make that balance by putting a 3 there. And then oxygens, which is where I'm predicting my difficulty, I have got 2 on the left, and then I've got 2 times 2, that's 4, plus another 3, that's 7 there. So I'm going to have to multiply this guy by 7 on 2. Now, we don't want to have fractional coefficients. We need the smallest whole number set of coefficients, so we're going to multiply everything by 2 here. So that will get rid of our fractional coefficient. So that's going to become 4, that's going to become 6, that's going to become 2, and that guy is going to become 7. And there we are, all balanced. 2, 7, 4, 6. We know it's the smallest whole number ratio because you can't divide through by a common multiple. Okay. So this looks like we're going to classify reactions as combination, decomposition, or single or double replacement reactions. So a combination reaction is multiple things coming together to form a single product. So multiple things coming together to form a single product, there's only one there. So that's that guy. Decomposition is one reactant forming multiple products. So that's that one. Yeah. Single replacement is an element reacting with a compound to form a new element and a new compound. And we have none of those. And then double replacement is two compounds reacting to form two new compounds. So that's what that guy is there. That's a double. Now notice that sometimes people will call combination synthesis, and sometimes people will talk about replacement reactions in the same way that we talk about displacement reactions. So that's just what we call synonyms, two words that mean the same thing. You'll kind of get used to it, you sort of have to. Alright, let's have a look at this one. Okay, so in this case we have to classify reactions according to the categories that we saw before, but also according to whether they are a precipitation, combination, combustion, or acid base. So precipitation means solid forms. So that guy's got a solid there in the products. That one hasn't. That one doesn't. And this one does. Combustion, O2 is a reactant, and we form an oxide. So let's go through here. No oxygen is a reactant, it's not a combustion. No oxygen is a reactant, it's not a combustion. No oxygen is a reactant, it's not a combustion. So it looks like none of the four are combustion. Nope, that's good. Alright, and then now the final new category we haven't seen previously in this video is acid-base. In an acid-base reaction, an acid reacts with a metal hydroxide to form an ionic compound and water. So we're looking for an acid plus a hydroxide, and it's going to form an ionic compound and water. So the first thing I'm going to look for when I'm kind of like thinking, is this an acid base, is I'm going to look for the presence of water. Water, no water, so not acid base, no water, not acid base. So now I'm going to consider the two that are in the middle there as possibly being acid base. So do we have an acid, and an acid. That's good. Do we have a hydroxide? 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 Do we have the water? Well, we always confirmed that. We already confirmed that. We have the water. Do we have an ionic compound? Ionic compound, ionic compound. So both of those two meet the requirements for acid base. So we've done that right-hand column now. We need to do the other categorization that we had before. So combination is multiple things coming together to form a single product. And the only one that meets that requirement is the last. No, it's not. Whoops, misread that. None of them meet that requirement. They all have multiple products. So wow, that was a little unexpected. We just had a little deviation there. So none of them are combination. There we go. Okay. Then single replacement is an element reacting with a compound to form a new element and a new compound. And none of these reactions involve the reaction of an element, so none of them are single replacement. Double replacement are two compounds reacting to form two new compounds. So we have that in the first case. We have it in the second case, we have it in the third case, but we only have one reactant in the fourth case, so that's no good. And then finally, decomposition is when a single reactant falls apart into multiple components. The only one that meets that criteria is the last one there. Okay, looking good. Okay, so in this type of problem, what you're asked to do is to finish off a chemical equation given some information. So we're told that ammonium salts heated with aqueous hydroxides form ammonia, water, and a salt. So when we say a salt, that just means the same thing as an ionic compound. So that's important to keep in mind. So what this is really saying is that an ionic compound containing the ammonium ion, when heated with a hydroxide, will form ammonia, water, and an ionic compound. So you do have to not use what you already know about chemistry to solve these guys. So that can be a little tricky. So we have to balance the following. So our ammonium salt, our ionic compound containing the ammonium ion in this case is ammonium carbonate, and it's an aqueous solution. And when ionic compounds are dissolved in water, they separate into ions. So this is going to separate out into two ammonium ions and a carbonate anion. And then our aqueous hydroxide is potassium hydroxide. And that's going to, because it's an ionic compound, that is going to separate out into potassium ions and hydroxide ions. And so this is going to go on and form ammonia, which we know the formula for is NH3, and water, and we know the formula for water is H2O, and also an ionic compound. So we have to figure out what's the ionic compound that's going to form. The ionic compound, hopefully you can see, is going to form between those guys, right? That's what's going to happen there. So when potassium, with its single positive charge, combines with carbonate with its two negative charges, they're going to do so in a 2-to-1 ratio. So the ionic compound will be K2CO3. So we figured out all of the products now, so now we just got to get everything to balance. So let's see if we can do that. So it is our ammonium salt, which is ammonium carbonate, reacting with our hydroxide to form ammonia, water, and another ionic compound which we identified as being K2CO3. So there are a couple of things that you can see don't balance immediately, which my attention is drawn to. Potassiums, I've only got 1 on the left and I've got 2 on the right. So let's make that a 2. And then the other thing that really leaped out to me is that I've got 2 nitrogens on the left and I've only got the 1 on the right at the moment, so I need to make that a 2. So let's see how things look from here. Let's move on. I always like to do hydrogens and oxygens last, so we'll see how that goes. I've got 1 carbon on the left and I got 1 carbon on the right, so it would be best if I didn't have to mess with the carbons at all, because if I did, that would mess up my K2 and my carbons. And then now I'm going to move on to my oxygens. So on the left I've got 3 plus another 2, so that would be 5. And then on my right I've got 3 plus another 1, so that would be 4. So if I put in a 2 there, that would be 3 plus 2, which would bring that up to 5. So that would be right. And let's see where we're now with hydrogens. So I've got 2 times 4, that's 8, plus another 2, that's 10. And then over here, 2 times 3, that's 6, and then 2 times 2, that's 4, so that's another 10 as well, so that's balanced. So relatively complicated. 1, 2, 2, 1 are my coefficients there. Okay, now everything in this case is going to be dissolved in water, so that's going to be AQ. Now water dissolved in water we just call liquid water. And then this is an ionic compound dissolved in water, so that would be AQ, right? So there was water all the way through here. So there we go. All right, good. Okay, moving on. Okay, so this is all about interpreting a reaction energy diagram. So what we see is we have our reactants are getting converted into products, but it has to go over the activation energy. So you always want to be careful that you read the scale well. So the reactants start off at 150, and then it goes up to get to the peak of the activation barrier, which is 250, and then it goes down to the products, which are at 100. Okay, so just making sure I got my values established there. So then it asks, what is the heat of reaction? So the first thing to recognize is that the products lie at lower energy than the reactants. So this reaction is losing energy, losing heat. Okay, so it needs a negative sign for the heat of reaction because of that. And we're going from 150 down to 100. So that means that 50 kilojoules was lost. Okay, so the heat of this reaction is negative 50 kilojoules per mole. So reactions that lose energy are referred to as exothermic. So exothermic reactions always have a negative heat of reaction. So can we determine the activation energy? Yes, it's just the difference between where our reactants are and this hill it has to get over to go on and form the product. So to do that, it has to go from 150 to 250 kilojoules. So it has to have 100 kilojoules of energy. Right, so it has to have that available to it in order to do that. Okay. What about if we wanted to go the reverse direction? What would be the activation energy? Well, that would mean that I'd have to go from 100, where the products are, up to 250. So 100 up to 250, that's a change of 150. So the activation energy for the reverse reaction is a lot higher. It's a third higher. Okay, good. So that concludes the objectives. So now we'll start working on the practice quiz. So what we've got to do here is classify reactions. So what I immediately notice about this reaction here is that there is one product. So that means it is a combination. In the second reaction, what I immediately notice is it's an element reacting with a compound to form a new element and a new compound. So that is a single displacement. In this third reaction, I've got two compounds reacting to form two new compounds. So that is a double displacement. And in this final reaction, I have a single reactant breaking apart into multiple products. So that means that it is a decomposition. Looking good, huh? Okay, we've seen this problem before. We have to tally up the hydrogen atoms on the right-hand side of this equation. So hydrogen is present at two different places. In this compound here, we have 3 units of that compound, and each unit contains 3 hydrogen atoms, so we've got 9 for that guy. And in this compound here, there are also hydrogen atoms. We've got 8 units of the whole compound, and in each unit of the compound, there are 4 hydrogen atoms, so that gives me another 32 hydrogen atoms, so a total of 41 hydrogens. If you tally up the hydrogens on the other side, you should get the same number, and that's well worth doing as a double check. Alright, this is one of those where you have to finish off the reaction. It said, did you know alkali metals and halogens combine to form halides? So in this case, we're forming barium fluoride. So that means that the metal that was reacting was barium, and barium is a solid. It's also a monatomic element. So that's the metal. What about the halogen? Well, the halide is the fluoride, so the halogen, it must be fluorine. And fluorine is a diatomic element, and it's a gas. So that's how it's going to look. All right, so you've got to be aware of the physical states of the elements, solids, liquids, gases, and you also need to know whether the element is diatomic or not. Okay. It says, balance the chemical equation below using the smallest whole number stoichiometric coefficients. Okay, so I'm just going to do this like working left to right because it's a pretty simple equation. It's only got 3 things in it. So nitrogen, I've got 2 on the left and 1 on the right. So I'm going to make that up to 2. And now they are balanced. And then hydrogens, I've got 2 on the left and I've got 2 times 3, 6 on the right. So I'm going to make that up to 6 by putting a 3 there. And now I am done. Not too bad at all. This is when we start moving into more complex problems, I'm sure of it. Okay, so this is reading an energy diagram. So we just got to be very careful with our numbers. So this has got markings every 50. So our reactants here are at 50. Then it goes to the top of our activation barrier, which is at 300. And then it goes down to our products, which are at 150. Just make sure. Yeah, okay, make sure you get those numbers correct. So what is the heat of reaction? It's the difference between the reactants and the products. So we go from 50 up to 150. So it's a gain in energy. So it's going to be a positive heat of reaction, and it's a change of 100. So make sure you get the sign correct. If there's a gain in energy, it's positive. If there's a loss in energy, it is negative. It says, is the reaction exothermic or endothermic? Well, it took energy in, so it is endothermic. Endothermic reactions always have a positive heat of reaction. Can you determine the activation energy? I can. It's the energy to go from the reactants to the peak of the top of the curve there. So that's 50 up to 300. So that's a change of 250. And then what about if we wanted to go back the other way? Could we figure out the activation energy? We could. We just got to use the values that we've got. So our products are at 150 and we got to get up to 300. So that's a gain of 150, isn't it? So, okay, there you go. All right, so not too bad. I'm feeling like we need something where we've got one of those big ones with lots of classifications of the reactions. And here it is. All right, we're just going to be very systematic. Are any of these precipitation? No solid, not precipitation. Solid, so it's a precipitation. Solid, it's a precipitation. No solid, it's not a precipitation. To check for combustion, I'm looking for the presence of oxygen in my reactants. Oxygen, oxygen, no oxygen, it's not combustion. No oxygen, it's not combustion. Okay, is it really combustion? Oxygen reacting with a compound to form an oxide, carbon dioxide. That is definitely a combustion. Sodium and oxygen forming sodium oxide. Definitely a combustion. All right, so that looks pretty good. All right, now we just got to check acid-base. Acid-base reactions always form an ionic compound and water. Not an ionic compound does have water, so it's not acid-base. No water in the products, not acid-base. No water in the products can't be acid-base. Water and an ionic compound in the products could be an acid-base reaction. That's an acid, perchloric acid, and hydroxides are bases. Base plus an acid gives ionic compound and water. Classic acid-base reaction. All right, now what do we got to do? We got to decide whether it's a combination reaction. Combination reactions are multiple things forming one product. Multiple products, not a combination. It is a combination. Multiple things coming together to form one product. Multiple products, not a combination. Multiple products, not a combination. Single replacement is an element reacting with a compound to form a new element and a new compound. This is not an element and a compound, so it is not single replacement. This is not an element and a compound, not single replacement. This is two compounds, not single replacement. Again, this is two compounds, not single replacement. Double replacement is two compounds reacting to form two new compounds. This is not a compound, so it's not double replacement. Neither of these are compounds, it's not double replacement. Compound 1, compound 2 reacting to form compound 3 and compound 4, it's a double replacement. Compound 1 reacting with compound 2 to form compound 3 and compound 4, it's a double replacement. Decomposition is where one reactant breaks apart into multiple products. And all of our things here have more than one reactant, so none of them are decomposition. So that's probably the trickiest question amongst this set. Okay, now we've got to balance this chemical equation here. This is a combustion reaction, does have a diatomic element in there, could potentially be interfering coefficients. So CH4 plus O2 gives CO2 and water. So carbon, we've got 1 on the left and we've got 1 on the right. Hydrogen, 4 on the left, 2 on the right. Let's get it up to 4 by putting a 2 there. Oxygen, 2 on the left, 2 plus another 2, 4 on the right. So we're going to need a 2 in there. And now everything is balanced. So it's 1, 2, 1, 2. Nice and easy. Okay, what is the total number of nitrogen atoms on the right-hand side? So we've got two compounds containing nitrogen on the right-hand side. There's the arrow. So in the first one, we got 1 unit of the compound, and each unit contains 1 nitrogen atom. And then over here, we've got 2 units of the compound, and each unit contains 1 nitrogen atom. So 1 plus 2 gives me 3 nitrogens. Now, it should be the same on the left-hand side if this is balanced. So I've got 3 units there of the compound, and each unit contains 1 nitrogen. So I've got 3 nitrogens on the left as well. So that makes me feel really happy. Okay, guys, that's me running through the objectives and a practice quiz. So I hope you found that helpful. And yeah, let me know if you have any trouble. Okay, bye.